In this video, we are going to talk about alkenes, and then we also talk about how to name alkenes. In the last part of the video, we'll talk about geometric isomerism in alkenes. So what are alkenes? Alkenes are hydrocarbons with one or more double bonds. For example, if you take this cyclic ring, this is a cyclohexene. This is an example of an alkene. And then we can also have this. This is a cyclopentene. This is also an example of an alkene. And we can also have this example. And this is a 3-methyl 1-butene. This is also an example of an alkene. Now let's talk about the nomenclature of an alkenes. How do you name alkenes? For example, take this alkene. How do you name this alkene? Naming alkenes is similar to naming alkenes. So the first thing is to determine the parent chain. However, since it is an alkene, the parent chain must always contain the double bond. And you see that in this case, this becomes the parent chain because this is the longest chain that contains the double bond. Any other thing attached to the parent chain becomes the substituent. So, and we also need to determine the position of the double bond. And you can see that this double bond, the position is on carbon number 1. This is 1, 2, 3, and then carbon number 4. So on carbon number 3, we have a 3-methyl, and on carbon number 2, we have a 2-methyl. And therefore, the name of this alkene is 2,3-dimethyl. But the total number of carbons are 4, so it's butene. However, we need to show the position of the double bond. The double bond is on carbon number 1, therefore it becomes 1-butene. So what about this molecule? How do you name this molecule? The first thing is to determine the parent chain. What is the parent chain of this molecule? The parent chain is a chain that contains the alkene, the longest chain that contains the alkene functional group. So in this case, you can see that this becomes the parent chain because this is 1, 2, 3, 4, 5, 6. Now, we need to assign numbers to the various carbon atoms. So this is carbon number 1, carbon number 2, carbon number 3, number 4, number 5, and number 6. And since there are 6 carbons, then the name is a hexene. However, we have the double bond on carbon number 2, so it is a 2-hexene. And then this is a tet-butyl substituent on carbon number 3, so we have a 3-tet-butyl. And then we also have a methyl substituent on carbon number 2, so a 2-methyl. And then the parent name is hexene. However, the double bond is on carbon number 2, so it is a 2-hexene. And therefore, the name of this molecule is 3-tet-butyl 2-methyl 2-hexene. So let's consider this molecule. Try naming it. You can pause the video at this point and try. You can see that this substituent is an ethyl substituent, and it is on carbon number 1 of the cyclohexene. And therefore, this is 1 ethyl, then 1 cyclohexene, because this one is showing the position of the double bond. The double bond is on carbon number 1. Let me write the name here. It is 1 ethyl, 1 cyclohexene. Let's also consider this molecule. You can pause the video and try naming it. So let's assign numbers to the carbon atoms. This is 1, 2, 3, 4, 5, 6, and 6. So because there are 6, this is cyclohexene. However, there are two double bonds, and therefore it is a diene. We need to indicate the positions of the double bond. The double bond is on carbon number 1 and carbon number 4. So this becomes a 1,4 cyclohexadiene. Now let's also name this molecule CH3C double bonded to a CH, and then there's a substituent here, a chlorine. Try naming this compound. Now you can see that this is the longest chain. However, there are two double bonds in this molecule, so it's going to be a diene. So let's number them. This is number 1, number 2, 3, 4, 5, and 6. So it is a hexadiene. However, we have the double bond on carbon number 1 and carbon number 4. And we have a chlorine substituent on carbon number 3. So it becomes 3 chloro. Then the double bond carbon number 1, carbon number 4. So it becomes 1,4 hexadiene. What about this molecule? What is the name of this molecule? So let's identify the parent chain. We said the parent chain is the chain that contains the alkene, and this is a diene. So you see that this becomes the parent chain. And therefore, this becomes carbon number 1, carbon number 2, number 3. Sorry. The double bond begins on the first carbon. So we need to give precedence to the double bond. And therefore, this rather becomes carbon number 1, number 2, 3, 4, and then number 5. So you see that this becomes a substituent, which is a cyclohexyl substituent, and we also have an ethyl substituent. So the cyclohexyl substituent is on carbon number 5, so it becomes 5 cyclohexyl. Then 3 ethyl substituent is on carbon number 3, so it's a 3 ethyl. Then the double bond is on carbon number 1 and carbon number 3, so 1,3 diene. So it is 5 cyclohexyl, 3 ethyl, 1,3. And what is the name of this molecule? You can pause the video and try. So this is carbon number 1, carbon number 2, number 3, number 4, 5, 6, 7, 8, 9, and 10. So this is the decene. However, there are two double bonds, and therefore it is a diene on carbon number 1 and carbon number 5. So this is 1,5 decadiene. In naming alkenes, there are some special names that we must be conversant with. The first one is the vinyl, and the vinyl is H2C double bond CH, which is joined to an organic molecule. The second one is the allele, and then the allele is H2C double bond CH, and then CH2, which is joined to an organic molecule. The third one is the allene. The allene is H2C double bond C double bond CH, which is linked to an organic molecule. So let's name this organic molecule. You can see that this is a 6-membered ring with a double bond, so that is 1 cyclohexene. But there is this substituent here, and you can see that this is the vinyl substituent, and therefore this is 1 vinyl cyclohexene. So you can see that this is a vinyl substituent. This substituent. So the name is 1-vinyl 1-cyclohexene. So that is the name of this molecule. 1-vinyl 1-cyclohexene. What about this molecule? What is the name of this molecule? You can see that we can start numbering from here. 1, 2, 3, 4. So it's a cyclohexane group that has double bonds, 2 double bonds at carbon number 1 and carbon number 3. And then there is a vinyl group on carbon number 2. And therefore, this is 2-vinyl, then 1, because it's on carbon number 1 and carbon number 3. 3-cyclohexadiene. So the name of this molecule is 2-vinyl 1,3-cyclohexadiene. So let's also name this molecule. This is a double bond. So we'll give precedence to where the double bond is. And therefore, this is 1, 2, 3, 4, and then 5. So it is a 5-membered chain, and therefore that is a pentene. However, we have 2-methyl substituent on carbon number 4, and then the double bond is on carbon number 2. So it becomes 4,4-dimethyl. And then we need to show the position of the double bond. So it becomes 2-pentene. Let's talk about E and Z isomerism. E and Z isomerism is a way of showing the isomerism in double bonds. So geometric isomers can exist as cis or trans, as we have seen in previous videos. I'll provide a link to the videos on stereochemistry in the description below. So we have cis and trans isomerism. In E and Z, the cis stands for the Z, and then the trans stands for the E. Z means zusammen. Zusammen is a German word. And then the E means entgegen. The E stands for the trans, and then the Z stands for the cis. Let's consider this molecule. Will this molecule exhibit cis and trans isomerism? For a molecule to exhibit cis and trans isomerism, if you divide the molecule vertically and you look at either side, if you consider the sides, then the groups that are here must be different from each other, and then the groups that are also here must also be different from each other. No two of them must be equal. So the first thing, the easiest way to know is to divide the molecule vertically at where the double bond appears and check on both sides of the double bond and see whether the groups there are different. So the groups here must be different, and then the groups here must be different. And therefore, if you consider this molecule, you can see that this is a proton, this is also a proton. So this molecule will not exhibit cis and trans isomerism. Will this molecule exhibit cis and trans isomerism? The answer is no, because if we divide the double bond into two and look on either side of the double bond, you can see that this is a methyl group, CH3, and this is also a CH3. And this CH3 is equal to this CH3, and therefore we will not have cis and trans isomerism. Let's consider this molecule. Will this molecule exhibit cis and trans isomerism? So the acid test is to divide the double bond into two and look at other side. You can see that this side is a CH3. It is different from this proton here. And then this side is also, this is a CH2. It is different from the proton here. and this side is also a CH2. It is also different from the proton here, and therefore if we look at this side, there are different groups, and on this side too there are different groups, and therefore this molecule will exhibit cis and trans isomerism. Let's go ahead and determine it. Now, the way to determine it is to check here. We use the atomic mass of the group that is joined to the carbon bearing the double bond to determine the geometric isomerism. So you can see that carbon has a larger atomic mass than the proton, and therefore here the carbon is ranked 1, and then the proton is ranked 2. In this case, it's the same thing. The carbon will be ranked 1, and then the proton will be ranked 2. And now you can see that if you divide this molecule horizontally, at the upper part it is 1, 2, and then the lower part is also 1, 2. So you see that the groups of higher priority are on opposite side of the horizontal line, and therefore this is a trans molecule. One is on top here, and then here one is at the bottom. So this is a trans. Therefore this is a trans isomer. Consider this molecule. Determine whether the molecule is a cis molecule or a trans molecule. The first thing is to divide the position of the double bond vertically and look on opposite side. If you come here is a CH2, this is a CH2. So you go to the next. This place is a CH2, but here is a CH joined to a metal group. And therefore you can see that other side of this double bond is different on this side. Then let's take this side. This CH3 is different from this ethyl group, and therefore this molecule exhibits cis and trans isomerism. Nonetheless, will it be a cis or a trans? So we'll divide this molecule horizontally at where the double bond is. And you can see that here is a CH2, and then this is a CH2. Then this is a CH2, and this is a CH3. So the down here becomes 1 of higher priority, and then the top here is 2. If we come to this side, this is a CH3, a methyl group, and this is an ethyl group. So the ethyl group becomes 1, and then the CH3 becomes 2. So considering the horizontal line, you can see that on this side, the lower side is made up of 1, 1, and then the upper side is 2, 2. So the groups of higher priority are on the same side of the horizontal line, and therefore this is a cis molecule. So this is a cis, and therefore it is a Z. Let's consider this molecule. Is this molecule a cis or a trans molecule? So let's divide this double bond vertically. On this side, you can see that the top is a proton, and then the down is a methyl group. The methyl group has a higher molar mass than the proton. So the methyl is given 1, and then the proton is given 2. Then here, this is an ethyl group. It is of higher preference than the proton, which is 2. So if we divide this double bond horizontally, you can see that at the upper part, the group of higher priority here is on top, and the one of higher priority here is at the down. So the groups of higher priority are on opposite sides of the molecule, and therefore this is a trans molecule. And since it's a trans, it's an E. So let's try and name the molecule. So we need to give precedence to this double bond, and therefore here is carbon number 1, number 2, number 3, number 4, and then number 5. So we are talking about a pentene, and then the double bond is on carbon number 2. However, we have the cis and trans isomerism on carbon number 2. So this is a 2E. We'll put that in brackets. 2 pentene. So now you can pause the video and try naming this molecule. What is the name of this molecule? The first thing is to determine cis and trans isomerism here. So there's a proton here, and then there is also a proton here. So divide the molecule vertically. On this side, here is an ethyl group, and therefore this is number 1, and this is number 2 for a proton. Then on this side, a carbon bonded to a chlorine becomes number 1, and then the proton becomes number 2. Then you divide the double bond horizontally. You can see that the one are on the same side of the horizontal line. 1 and 1 are on top of the horizontal line. Then 2 and 2 are also at the bottom of the horizontal line. So the groups of higher priority are on the same side. And therefore, since they are on the same side, it's a cis, which is a Z. So let's name the molecule. This is carbon number 1, carbon number 2, carbon number 3, 4, 5, 6, and then 7. So, but there is a chlorine on carbon number 5. So we need to show the position of the chlorine. So let me write the name here. So it is 5-chloro. And then we have Z isomerism on carbon number 3. So we need to first start with 3Z in brackets. Let me write it again. Let me write it at the top here. So we need to first start with 3Z in brackets. 5-chloro. So let me write the name here, down here. So it is 3Z, then 5-chloro. And the double bond is on carbon number 3. So carbon number 3, then the total number of carbons are 7. That is a heptene. So 3-heptene. So the name of this molecule is 3Z5-chloro 3-heptene.